Hello everyone, and welcome to some more Calc 2 remote learning. Today we're now going to actually get into working with these vectors in 3 dimensions, so no longer just working with vectors in that XY plane. So in 3 dimensions, well, 2 dimensions we know it was mostly XY. In 3 dimensions we're going to add a Z to that. So if you can envision our XY plane and another axis Z coming out of it. So if this was our XY plane, and then we have some Z as well, you can see that 3 dimensions. Now when drawing those coordinates in 3 dimensions, setting up our coordinate axis, we have to be conscious of the right hand rule. And what the right hand rule says is going to look a little backwards since I'm mirrored right now, but if you take your right hand, so this may seem like it's my left hand to you guys, but it's my right hand. If we take my right hand and curl it, we're going to go X to Y to Z. So if I was to label this curling going from X to Y, my positive X is going to be here, my positive Y here, and then my positive Z here. So if you can envision curling around from X to Y with my positive Z going up. That's that right hand rule, and that's how we're going to set up our coordinate system. Now, the nice thing about being on the computer is I'm going to make this a lot neater than it is, or than it appears. So there you can kind of see my X, Y, and Z axes. So we took our familiar XY plane and added a third axis, that Z axis. So we went from working in 2 dimensions with quadrants to now working in 3 dimensions. Now we have octants, where that first octant is positive X, positive Y, and positive Z. So if you can envision splitting up this shape up into 8 different pieces. And we can see those different octants divided and created by the different coordinate planes. And those 3 coordinate planes are the XY plane, the XZ plane, and the YZ plane. Now, for the XY plane, we've been working with that a lot. When we were working with that XY plane, Z was 0. So the XY plane, a simple equation is Z equals 0. And you can see when Z is 0, we're dealing with the XY plane. Now the XZ plane is, well, if we only have X and Z values, that means that our Y has to be equal to 0. So the XZ plane, if Y was 0, this is our Y axis along here, and Y is 0, so it's not going to move along this axis. So we'll simply have our plane there, and you can see that that's just that slice. If I was to essentially look at XZ without Y, it's just that slice that's perpendicular to Y, but it does not move along Y because Y is 0 for that XZ plane. And same concept for YZ plane. What variable do we not have in there? X. So X is going to be set as 0. So if we're looking at our X axis and we're setting that as 0, we're not going to be moving from that point. We're not moving towards or away from us, so we're going to have this plane here. Another slice where X is constant. So we could easily make another plane by setting X as, let's say, a positive value of 2. So if I moved 1, 2 along that axis, if that was my spacing for my units, then we're not going to move from X equaling 2. So we have the plane, but that plane, remember, is perpendicular to that X axis, but we're moving parallel to that X axis. So we're just going to move our plane up to that point 2 in that X axis. So hopefully this visual gives you an idea of how to work with planes. When we get into a later video, we're going to start going over equations for plane. But these were simple coordinate planes, which are fairly easy to visualize and work with. Now let's get into actually plotting some points. So we're going to use this coordinate system I've set up above to plot the points P and Q, where P is the point 3, 0, 0, and Q is the point 0, 2, 0. So let's think about labeling this quickly. If I did X, remember positive X is coming towards me, so I'll do X of 1, 2, 3, and 4, and then we'll have negative 1, negative 2, negative 3, negative 4. So I'll put 1 to 4, 1 to 4, and those are negatives, where that origin is that point 0, 0, 0. So Y's, we'll do 4 again, so 1, 2, 3, 4, and a negative 1, 2, 3, 4. And then lastly, we'll do Z, so that'll be 1, 2, 3, 4, and 1, 2, 3, negative 4. So with this, hopefully you can get a feel for how we're going to plot these points. So I'll make point P in green, and we have it at 3, 0, 0, X, Y, Z. So that's 3 in the X, so 1, 2, 3, 0 in the Y, so we're not moving right to left, and we're not moving up and down. So that's going to be this point here, 3, 0, 0, which is point P. Now point Q, I'll go ahead and do in blue, and that's 0, 2, 0. Again, X, Y, and Z. So we're 0 in the X, so we're not moving towards us or away from us. So we're going to fall somewhere in that YZ plane. And Z is also 0, so we're not going up or down, but Y is a positive 2. So we're at this point Q of 0, 2, 0. So that's how you work in 3 dimensions. X, comma Y, comma Z, plotting the same as 2 dimensions, except now we have that 3rd dimension we're working with. Now in part B, it says to sketch the plane that passes through the points in part A, so that's going to be PQ, and it's going to pass through R of negative 1, 1, 4. So before we plot negative 1, 1, 4, let's think about a plane. If I told you to go ahead and make a plane right now given these 2 points, well, we're not quite sure of, let's just call it the tilt of the plane, because I could draw that plane vertically, or I could draw that plane horizontally, or I could draw it at an angle. So I could have that plane going perpendicular to Z, I can have it running parallel to Z. And if we think about it, if I drew that plane horizontally, since Z is 0, that's essentially just going to be that XY plane. But once we add this 3rd point, we will just connect those 3 points to form our plane. Our point R was negative 1, 1, 4. So negative 1 in the X, moving back 1, 1 in the Y, so moving a positive 1 to the right, and then up 4, 1, 2, 3, 4, will be at this point here. Negative 1, 1, and 4. Now sometimes it's a little difficult to see points in 3 dimensions, so I recommend labeling all your points. So now if we were to draw that plane, the easiest way to do that would be to connect our 3 points to form a triangle, but remember that expands out in all directions. So we have some triangle, if you can envision that plane, but expanding out in all directions. Like if we were taking a slice and cutting it with a knife, hitting each of those points, that would be our plane. Now, working with vectors in 3 dimensions is similar to working with vectors in 2 dimensions. To find the length of some vector, remember, in 2 dimensions, that was the x component of our vector squared plus the y component of our vector squared and the square root of that sum. Same concept in 3 dimensions, except now we're also going to add that z component of our vector squared. So the 1st, 2nd, and 3rd components all squared, summed together, and the square root. And in order to create vector PQ, remember it's head minus tail. So PQ is going to be 0 minus 3, head minus tail for the first component, 2 minus 0, head minus tail for the second component, and 0 minus 0, head minus tail for that third component. So this is going to be -3, +2, 0 for our vector PQ. So you can see, essentially, we don't even have a third component that we have to worry about. Because remember, that vector PQ, if we were to look at this, PQ falls in that xy plane. So all we would need to do to find that magnitude is to take the square root of -3 squared plus 2 squared, and I'll go ahead and throw this 0 squared in there, but 0 squared is 0. So you can see that because we fell in that xy plane, it was just the x component squared plus the y component squared and the square root of that to find those distance or that length. So this is going to be the square root of 9 plus 4, which equals the square root of 13. That's our magnitude of vector PQ. But now let's see how it comes into play when we have a vector that does not fall in that xy plane. So the length of vector PR. Well, first, let's solve for that vector. PR, remember, head minus tail. So we're going to take the components of R and subtract those components of P. So the first component of R is -1, so we'll have -1 minus 3. And then we'll have 1 minus 0, and then a 4 minus 0. Head R minus tail P. So this is going to give us -1 minus 3 is a -4, 1 minus 0 is 1, and 4 minus 0 is 4. So -4, 1, 4 is our vector PR. So there's PR, and there was PQ. And you can kind of see that vector. If we started at P and went to -4 in the x, 1, 2, 3, 4, and then we went a +1 in the y, and then a +4 in the z, we'd be at that point R. So PR is -4, 1, 4. And the length of that is going to be the square root of those components squared. So -4 squared plus 1 squared plus 4 squared. So that's going to be 16 plus 1 plus 16, which is going to be the square root of 33. So if I was to write the magnitude as a formula, it's going to be, let's say, some vector v, where that vector v is v1, v2, and v3 for the components. It's the square root of v1 squared plus v2 squared plus v3 squared. Which, if you think about, when we're having two different points creating that vector, it's the change in x squared plus the change in y squared plus the change in z squared. So helping us use that Pythagorean theorem to get that distance of the hypotenuse for our triangle. We did that with 2 dimensions, and that concept can be expanded upon in 3 dimensions. Because finding the distance between that head and tail is the same as finding the length or magnitude of our vector. So operations previously learned with 2-dimensional vectors also applies to vectors in 3 dimensions. So let's practice summing these. So if I have vector u as 2, -1, 5, and vector v as 0, 3, 1, adding those together, I'm going to have u plus v, which is 2, -1, 5, plus 0, 3, 1. Remember, we add the like components together. So our first components get added together, then our second components get added together, and our third components get added together, each to make component 1, 2, and 3 respectively for our new vector. So we'll do 2 plus 0, and then -1 plus 3, and then 5 plus 1. So vector u plus v will be 2, 2, and 6. Because 2 plus 0 is 2, -1 plus 3 is 2, and 5 plus 1 is 6. So we went over summing vectors, so vector addition. We can also scale vectors by multiplying, and we can also do vector subtraction, because subtraction is just adding that negative. And remember, for scaling vectors, we're going to multiply that scalar, which, remember, a scalar is just a real number. We're going to multiply that into each of the individual components in our vector. So for 2u minus 3v, we'll do 2 times 2, -1, 5, and we'll subtract 3 times 0, 3, 1. 2 times 2 is going to be 4. 2 times -1 is going to be -2. 2 times 5 is going to be 10. So 2u is 4, -2, 10. And then I'm going to be subtracting, multiplying 3 to vector v. 3 times 0 is 0. 3 times 3 is 9. And 3 times 1 is 3. So now I'll just subtract those. 4 minus 0 is 4. -2 minus 9 is going to be a -11. And 10 minus 3. Now let's talk about some coordinate unit vectors so that we can expand upon this concept. Well, first of all, what's a unit vector? Remember, a unit vector is a vector with a length of 1. So if we're doing coordinate unit vectors, we want a vector with a magnitude or length of 1 in the direction of one of our coordinate axes. So I, if you remember in 2 dimensions, was 1, 0. But now in 3 dimensions, still having a length of 1, we're going to do 1, 0, 0. For x, y, z, 1 in the x, 0 in the y, 0 in the z to form that vector 1, 0, 0. So then we're going to have j, if you remember from in that xy plane, that was 0, 1, but now we're doing it in 3 dimensions, so 0, 1, 0. And you can see, again, they're both unit vectors because if we take the magnitude, that's going to be the square root of 1 squared plus 0 squared plus 0 squared, which is the square root of 1. And then for j, the square root of 0 squared plus 1 squared plus 0 squared is also the square root of 1, which equals 1. Now remember, we're in 3 dimensions, so we have another coordinate unit vector, and that's the one in the z direction. So this, k, is going to be 0, 0, 1. So if you can envision these vectors in 3 dimensions, here's my y-axis, x-axis, z-axis, remembering to label accordingly to the right-hand rule. If I started all of these vectors at the origin, I would be 1, 0, 0, j would be 0, 1, 0, and k would be 0, 0, 1. I, j, and k. So in example 4, we're going to deal with magnitude and unit vectors. Given points P, 1, 6, 12, and R, 4, 10, 13, we're going to express vector PR in 2 different forms. Vector notation, A, B, C, and by using our coordinate unit vectors. A scalar times vector I plus a scalar times vector J plus a scalar times vector K. But before we do this, we need to find exactly what vector PR is. And remember, we do that by head minus tail. So PR is going to be 4 minus 1, 10 minus 6, comma, 13 minus 12. So in that first form, that's going to be 4 minus 1 is 3, 10 minus 6 is 4, and 13 minus 12 is 1. Now writing this in the form of A times vector I plus B times vector J plus C times vector K, Remember, because these are coordinate unit vectors, they each only have, well, I only has an x component, j only has a y component, and k only has that z, or that third component. So we're going to have 3 times I plus 4 times j plus 1 times k, or simply k. 3, 4, 1, you can see I just multiplied each of those to the appropriate coordinate unit vectors. 3i plus 4j plus k for part A. Now let's find that length or magnitude of PR. So that's going to be the square root of 3 squared plus 4 squared plus 1 squared, which gives us the square root of 3 squared is 9, plus 4 squared is 16, plus 1 squared is 1. 9 plus 16 is 25, plus 1 is 26. So that's the square root of 26. So in part C, it instructs us to find 2 unit vectors parallel to PR. Now remember, what does parallel mean? Parallel is just a scalar multiple of that vector PR. So essentially what we're going to do is we're going to make PR into a unit vector, because that unit vector was created by multiplying by a scalar. So remember, to create the unit vector, it's going to be vector PR over its own magnitude, because if we take this vector and divide by its length, that's going to give us a length of 1. So I'm going to have PR, which is 3, 4, 1, and I'll divide it by the square root of 26, which dividing by the square root of 26 is the same as multiplying by 1 over the square root of 26. So all I'm doing is taking vector PR and multiplying it by a scalar. So this vector is still parallel to PR, and it also happens to be a unit vector because the length is 1. So this will be 3 over root 26, 4 over root 26, and 1 over root 26. So there we have one vector parallel to PR that's also a unit vector. And remember, vectors have direction and magnitude. So the magnitude has to be that same, that length of 1, but the direction can be different because we just want it to be parallel. So this is a unit vector in the same direction as PR. Now I'm going to make a unit vector in the opposite direction. So I'm not going to change that magnitude. I'll just multiply by a -1. So then I'll get that vector, that's the unit vector parallel to PR, but in an opposite direction of PR, however, still parallel. So then I'll have some vector, -3 over root 26, -4 over root 26, and -1 over root 26. There's another unit vector parallel to PR. This one just happens to be in that opposite direction. And lastly, for this example in part D, it says to find 2 vectors parallel to PR. So again, without even reading the rest of the question, we know that we're going to be multiplying vector PR by some scalar because we're parallel to it. And we want those 2 vectors to be 3 times the length. So think about it. We've already created a unit vector that has a length of 1. All we need to do is multiply that vector by 3 to get a vector parallel to PR with a length of 3. And because we need 2 vectors parallel with the same length, remember vector is direction and magnitude, that magnitude has to be the same, so we have to keep it at 3, but our direction can be opposite. So I'm just going to take my unit vector and multiply it by 3. And I can take each of my unit vectors and multiply them by 3, because then I'll get that same direction and the opposite direction, both with a length of 3. Or you can think about just taking our positive unit vector and multiplying it by a 3 and a -3. So this is going to be 9 over root 26, 12 over root 26, and 3 over root 26. There's a vector with a length of 3, and this one goes in the same direction as PR. And now I'm going to do the opposite of that. So I'm going to multiply that by -1 to get -9 over root 26 negative 12 over root 26, and negative 3 over root 26. What I recommend is to do a quick double check. Take the magnitude, using our magnitude formula, of either of these vectors and see, is that magnitude indeed equal to 3? So go ahead and give it a go. But let's continue on to the next page. In the next page, we're going to be going over spheres and balls in 3 dimensions. If you remember, in 2 dimensions, we were working with circles, and circles were x minus some center x naught squared plus y minus some center y naught squared was equal to our radius squared. That was a circle, and we really dove into that when we went over parametric equations. But if I'm trying to now create a sphere or a ball in 3 dimensions, I'm just going to expand upon this concept. So remember, we were centered at x naught, y naught when dealing with a circle. But now, as opposed to using x naught, y naught, I'm going to be using a, b, and c. So I'm going to have x minus a squared plus y minus b squared. And can you guess what else we're going to add? That's going to be our 3rd dimension, z minus c squared, and that's still going to be equivalent to r squared. That gives us a sphere. Now a ball, technically in 3 dimensions, is that sphere and including everything enclosed within it. So I think of a ball as a solid sphere, whereas a sphere itself is just that shell. That ball is that sphere and everything contained within. So we're going to have the same formula essentially, x minus a squared plus y minus b squared plus z minus c squared, except now if I want everything contained within, a ball is going to be an inequality. So that's going to be less than or equal to r squared. So that's the only difference. So knowing our different formulas, let's go ahead and complete example 5. In example 5, it says find an equality or an inequality that describes a ball with center negative 1, 2, 5, and a radius of 1. Right away, because we're describing a ball, that means that we're dealing with what? An equality or an inequality? A ball is an inequality. So I know I'm going to be in the form of x minus a squared plus y minus b squared plus z minus c squared is less than or equal to r squared. And it tells me my center. There's my a, b, and c, and my radius is 1. So let's just go ahead and fill in our blanks. We'll have x minus a negative 1, so that's going to be x plus 1 squared, plus y minus b, so y minus 2 squared, plus z minus c, which c is 5, squared is less than or equal to our radius squared, r squared, which is 1 squared, and 1 squared is simply 1. So that's an inequality that describes a ball centered at negative 1, 2, 5 with a radius of 1. In example 6, we're going to find an equality or an inequality that describes a sphere with center 1, 3, 2 passing through the point 3, 5, 3. So right away, we're describing a sphere, and a sphere is an equality. So we know we're going to be dealing with the equation x minus a squared plus y minus b squared plus z minus c squared equals, because we're dealing with a sphere that's an equality, r squared. Now it gives us our center, a, b, c, as 1, 3, 2. What it doesn't give us is our radius. However, we can solve for our radius because we know if we're centered here and our sphere passes through this point, we can find the distance from our center to that point, and that's going to be our radius. Just because we've been working with vectors a lot on this worksheet, let's make this center point P, and let's make this point Q. So if we were to try to find that distance, we want to find the length of a vector. So let's go ahead and make vector PQ and find its magnitude, and that'll be our radius. So vector PQ is going to be head minus tail. So that's 3 minus 1, 5 minus 3, and 3 minus 2. So that gives us 2, 2, and 1. So now finding the magnitude of PQ, that's going to be the square root of 2 squared plus 2 squared plus 1 squared, which is the square root of 4 plus 4 plus 1. So that's the square root of 4 plus 4 is 8, plus 1 is 9. The square root of 9 is 3. So that magnitude, that length 3, is equal to my radius r. And you didn't have to necessarily set PQ up as a vector. You could have just used those x, y, z coordinates from each and still solve without setting up the vector, just by calculating the distance between the points. Essentially, you go through the same process. I just set up a vector since we were used to finding the magnitude of vectors. So now that we have all our components, we have A, B, C, and we have R, let's go ahead and write our equation for a sphere. So x minus 1 squared plus y minus 3 squared plus z minus 2 squared is going to be equal to r squared, which r was 3, so that's equal to 3 squared. And 3 squared is 9. So there we have it, the equation of a sphere centered at 1, 3, 2, passing through the point 3, 5, 3. In example 7, it says to give a geometric description of the following set of points. Now, just as a hint, since we're working in the spheres part of this worksheet, this is either going to be a sphere or a ball. But I have an equation, so I know that I'm going to have some sphere. However, in order to give that geometric description, I need to know what it's centered at, and I need to know its radius, which I cannot easily tell from this equation. So what I'm going to do is I'm going to group my terms together, my x's, my y's, and my z's together. So I'll leave x plus 1 squared alone because that's already grouped together. But I'm going to write y squared with 6y and group those together. And then I'm going to write z squared with negative 4z and group those together. And then I have this 9. I'm going to move that to the other side of my equation. So that's going to be equal to a negative 9. Now remember, from our sphere equation, we're looking for x minus a squared plus y minus b squared plus z minus c squared equal to some r squared. So what we're going to do is we're just going to have to complete the squares among our y and our z terms. Since we already have that x minus a squared over here, we just have to complete the squared with y and z. So leaving x plus 1 squared alone. So how would I complete the square for y squared plus 6y plus or minus something else gives me a completed square? Well, because my coefficient of y squared is 1 and I have 6, all I need to do is divide that 6 by 2. 6 divided by 2 gives me 3. So you can see if I have y plus 3 squared, y plus 3 squared is really y squared plus 6y plus 9. And for z, all I have to do is divide that negative 4 by 2. So that's going to be z minus a 2 squared. So you can see if I was to write that out, that would be z squared minus 4z plus a positive 4. Now looking at this, in order to get y plus 3 squared, I added 9. And in order to get z minus 2 squared, I added 4. So because I added 9 and I added 4 to my left-hand side of my equation, I have to add 9, and I have to add 4 to my right-hand side of my equation. So -9 plus 9 is 0, plus 4 is 4. And there you have it. We're in the form for our sphere. So this is a sphere centered at, well, x minus a, so that's going to be -1 for a, y minus b, that's going to be a -3 for b, and then z minus c, that's going to be a +2. So our point is -1, -3, 2, and we have a radius of 2, because remember, r squared is 4, and the square root of 4 is 2. So the geometric description of this set of points is a sphere centered at -1, -3, 2, with a radius of 2. And with that, we wrap up this practice and example worksheet on vectors in 3 dimensions. Hopefully you learned some more information and expanded upon what you learned within your lesson. If you still have any remaining questions, please leave them in the comments below, and I'll be sure to get back to you as soon as I can. But until next video, good luck with your online learning.